Give me a minute, I need to make this call here.
Yeah. Let's give it a look. Here. Say what, did you? Yeah, just a little water bottle. So. Why would you do that? I just forgot it. Why did you forget? I don't know. Play with him. Right, there was some others that's got the ice cream. Like unironically, he got them. Not even thinking. Bro, how was the day only halfway done? Like that. It's like 5 days. Like Mondays or Wednesdays, I wake up and then I come back one of the time I come back home, it's dinner time. Wake up. And something come here, go to the gym, it's done. Yeah, that's like an 8. Yeah. So probably the first one on the right side. One of the good picks. Oh, pretty easy. Oh, wait. That's the piping energy? Wait. Yeah, that's so. All that. The sync fixes thing. That's how he does. So this is for the That's how X ones. Yeah, do it. Oh, okay. You're gonna have like a lot of sync fix. How much different? What is one? And I have 10 What one? Doesn't that run the? Yeah, but it's like so anyway, this is 360. If you just forget about the 68, it's 360. How does it become 460?
Okay, folks, sorry about that. So let's talk about more chemistry, more problems. Any questions you guys have? Any
Yes, 2 point whatever.
This.
So. Give it to this. It will be 3 seconds. Why would it 7.4? Because this says you
Share my screen.
So there'll be 3 decimal places.
Yeah.
Plus the whole number.
Yeah, really.
Okay, so any questions you guys have? Any more topics of interest? Anything you need explanation?
No, I'm just saying, so. So negative.
Or any questions? Yes, ma'am.
This
Two.
So you're talking about the pass final? All right, so let's see here. I think I saved it under pass test key, right?
Which is supposed to have 360.
And the final. Okay.
I'm asking them.
Is it what? 2, 3, 4. Another form is for the blending energy. It's like easy with MC squared.
And you say question number
5C.
5C.
Yeah, they use the FC squared. Yeah. So where do they come from?
5C, okay. So question 5C says, if 20.0 mils of 0.10 M barium nitrate are added to 50.0 mils of 0.10 M sodium carbonate, will a barium carbonate precipitate from that mixture, right? So the first thing okay, just to remind you, when it comes to predicting precipitation, remember we said that precipitation will occur if QSP in this case is greater than KSP, right? So upon mixing, right? If you calculate the concentrations of the barium ions and the carbonate ions, and then you put the concentrations into the QSP expression and compare it to the actual KSP value. If QSP is greater than KSP, that means precipitation will occur. If QSP is less than KSP, then there'll be no precipitation. Okay, so what I did here is that I first decided to calculate the concentration of the barium 2 plus upon mixing, right? How do I do that? Well, you start off with 20 mils of the 0.10 M barium nitrate, but the total volume would be 20 plus 50 mils, right? So basically you're diluting the barium ions in terms of the concentration from 20 mils to 70 mils. So the equation we're using here is C2 is equal to C1 V1 over V2, right? So in this case, your C1 would be the 0.10 M of the barium solution. V1 would be the initial volume, which is 20 mils, and V2 would be the final volume, which would be 70 mils, right? And I did something unnecessary here. I didn't even need to do any conversions from milliliters to liters. So this here and this here is not necessary, not wrong, right? But not necessary, right? So you don't need to convert the milliliters to liters, because as long as the units here and here are the same, then the result would be correct, right? In any case, this is what I got when I did that calculation, all right? 0.029 M for the barium 2 plus. And then I do the same thing, let me clear this here. I do the same thing for the carbonate ion down here. But this time it's 50 mils of the carbonate times its molarity, which is 0.10, divided by the same volume here, and that gives you 0.071 M, right? And then based on those two concentrations, I calculate QSP, right? QSP is equal to the concentration of barium 2 plus times the concentration of carbonate. And that gives you 2.1 times 10 to the minus 3 when you plug the numbers in. And then, of course, what I would have to do is consult the tables, which you'll have access to find what the KSP value is. So when I did that, I got 2.58 times 10 to the minus 9. So basically, when you compare this to QSP, obviously QSP is greater than KSP. And therefore, you can say that precipitation will actually occur as a result of mixing these two solutions together. All right? So whenever it comes to predicting precipitation, first thing you should do is try to find QSP first, and then you look up KSP, and then you compare the QSP to KSP. Yes, sir?
If QSP was equal to or less than KSP, it won't form, right?
QSP must be, if QSP is less than KSP, no precipitation will form. Now, if QSP is equal to KSP, that means that no precipitation as well, actually. The solution is saturated. Right. Okay, any other questions? Yes, ma'am.
Solution would you find the KSP for?
I'm sorry?
When you're finding the KSP, which solution would you find it
Oh,
for?
the KSP is for this precipitate that is formed. And the question says that the precipitate formed is barium carbonate. So you go to the table and look for barium carbonate, and you look up the KSP for that, and that would be how you get a KSP. Yes, sir.
Are you able to go to part B of this question?
Oh, you want to do part B?
Yeah, I just had a question on something.
Okay, but okay, just let me just ask. So are we all understanding part C? Any more questions about part C? All right. Okay. So you're saying now you want to do part B. Okay. Now part B is asking for you to calculate the pH at the equivalence point for the following titration, and the titration is 0.10 M formic acid versus 0.10 M sodium hydroxide.
Yeah, I was just wondering where you got the concentration of the under the base, the 0.050. I didn't see where you got that one.
Okay. Yeah, I'll show you. I'm surprised I didn't have it here. Hold on, let me see here. I thought okay, so let me explain how we got the 0.050, all right? So basically at the equivalence point, remember what the equivalence point is. It's a point where the amount of base that is present is stoichiometrically equal to the amount of formic acid that is added to it, right? So basically, we don't know what the volumes are. They didn't give you any information about the volumes, right? But basically, what we know is that because the molarities are the same, 0.10 m here, 0.10 m here, that means that the volumes would be equal. Whatever the volume would be at the equivalence point, they're equal to each other, right? So basically, if the volumes are equal, that means that when you mix them together, the molarities of these will be halved because of the inverse relationship between the molarities and the volume. Now, the reaction that is taking place is this reaction right here. That would be HA, which is the formic acid, plus sodium hydroxide to give NaA plus H2O, right? So we know that, again, we don't know what the volumes are, but whatever the amount of this is reacting with this, which will be stoichiometrically equivalent, the number of moles of this will be the same, but the volume would be doubled, right? So therefore, we can come to the conclusion that because the volume is doubled, the concentration of this, which would be initially 0.10, but because the volume is doubled, that means that the concentration of A minus would be equal to half, I'm sorry, not half, but yes, half the concentration of the HA or sodium hydroxide, which would be half of 0.10, which would be equal to 0.050 m, right? So basically at the equivalence point, the volume would be doubled, which would mean that the molarity of the A minus would be halved, all right? Initially, the A minus, you'd expect it to be 0.1 because you start off with 0.1 of the acid, 0.1 molar of the base. So you expect to get 0.1 molar of the sodium formate, right? But because the volume is doubled now, you know that, well, that means that the molarity would be halved as a result. So that's where we got this 0.050 m from, all right? So, and therefore from here, I think you guys should know what's next. The A minus is the conjugate base, so therefore it's going to act as a base when it is hydrolyzed by water. Let me clear this here. Okay, so of course you set up your ice table, and of course you plug in your values for the different terms at equilibrium, and then you assume that X is small. And again, this is one of those situations where you will not find the Ka value, or I should say the Kb value for the formate ion, but of course, you can find the Ka value for the formic acid. So that's why we do this right here. We divide 1.00 times 10 to the minus 14 by the Ka for formic acid. That gives you 5.6 times 10 to the minus 11. That would be equal to X squared over 0.050 because we assume that X is much smaller than 0.050. And then we solve for X, and it turns out that X is equal to 1.7 times 10 to the minus 6. Again, as usual, we determine the percent dissociation by dividing 1.7 times 10 to the minus 6 by the initial molarity, and that gives you a number which is obviously less than 5%. So therefore, we can go ahead and say that the concentration of the hydroxide is 1.7 times 10 to the minus 6. Then we do the pOH to find ultimately the pH. So the pOH is minus log of that number. That works out to be 5.7, which means that the pH is equal to 14.00 minus 5.77. And I think that's it. That's what the question is asking for. Yes, sir.
How do you know the volumes are the same? Because couldn't it be like 50 ml of formic acid, like 100 ml of NaOH?
Well, that's a good question. All I can say is that that's the assumption that we have to make.
So like whenever.
But no, actually, that's not the correct answer. They would have to be the same in order for the equivalence point to be reached. Whatever the amount of one is, because the molarities are the same, right? Whatever the amount one is, the amount of the other must be the same in terms of the volume, right? Now, if the volumes were different, then your question would be pertinent, right? But because the molarities are the same, that means that the volumes would have to be the same for the equivalence point to be reached. And therefore, the total volume would be doubled. And therefore, the molarity of the A minus would be half of what the original concentrations of the HA and the sodium hydroxide is.
So what if the molarities were different?
Then some extra information would have to be given. You'd have to be given, for example, the volume of one And then you can find out the volume of the other, and then you can add up those two total volumes to get the concentration of whatever is remaining and so on. So additional information would have to be given in that particular situation, all right? Okay, any other questions about this problem? Yes,
So,
ma'am.
Professor,
Wait, hold on 1 minute, Mr. Medina. Yes, ma'am. Oh, the answer is down here somewhere, 8.23. Okay, Mr. Medina, you were saying?
so the HA and the NaOH have the same volume, correct?
The what?
The HA and the
Oh,
NaOH?
yeah, the same volume, right, exactly.
Okay,
Whatever
so
volume, you don't know what the volume is exactly, but they must be the same.
okay, and then with that, the A minus is half of
The
those two.
molarity of A minus is half because you're mixing two equal volumes. That means that the volume will be doubled, right? Which means that the molarity of the A minus would be half of the 0.10.
Oh, okay, because if it was molarity divided by the liters.
Exactly.
Okay, I get it now. Thank you.
All right. Okay, any other questions about this one or any other questions for any other? Here we go. Okay. Do I need to say something?
That's it.
Oh, okay. All right, thank you. I get no. Oh, don't worry. I guess I can get something.
All right, yeah, I'm sorry, they didn't tell me to bring it.
No problem, no problem, no problem. All right, thanks.
Have a good one.
Okay, folks. But when I say folks, I mean folks here in the classroom. Where am I gonna put these? I think I need to run upstairs and get some napkins and cups and so on. Okay, in the meantime, okay, so any other questions on this or any other topic? Yes, ma'am.
You go to question 1 on this.
Same exam? Question number 1 says,
For part B, I was
oh, part B, okay, hold on.
at the numbers, and whenever you were finding the moles of H2O, we ended up
Hold on.
getting,
Hold on. I think I discussed this earlier. And I think I corrected something. I don't remember exactly where I corrected it, but let me hear your question.
it's just that we start with 0.886, and then have 0.866.
Hold on. Okay, so we started off with this, and I think what I did next was find the mole fraction of water, which is this right here, 0.886, right? And then I tried to find the number of moles of water. So I did some algebraic maneuvers and I ended up with, well, actually, I was trying to find the number of moles of the sucrose, right? Which is this right here. And the number of moles of water would be the mass of the water divided by 18.02 grams. Right?
Yeah, I was just wondering if, because below that, after you started writing 0.866, and if that messed something up.
Did what?
0.866, does that change something?
Oh. So this should be 0.886. That's what it's saying. Yeah. Yeah, I think you're right. Yeah. So yeah, that's right. This should be 0.886. Here, here, here. So that will change the answer, I think. Let me see what that would give. Yeah, it just goes to show one slight mistake can screw things up. So 1 minus 0.886 divided by 0.886. And according to my calculations, this would work out to be equal to, okay, so I got here, instead of 0.155, I got 0.128, right? So this should be 0.128, which means that I'm going to multiply 0.128 by 552 and then divide it by 18.02. And according to my calculation, this works out to be equal to 3.92 grams. All right, so thank you, Ms. Weflin, for pointing that out. All right. Okay, I'm gonna make a quick run upstairs to get some stuff so that you guys can partake.
Think about this, bro.
That's the Chinese.
It's in China. Top 10. Top 10. Oh, Tata. Tata.
That's Zootopia.
It could be.
You want the class? He's closing the class.
Don't let me mess up. Ew. They ruined forget TikTok. They put Dave Portnoy in. You know Dave Portnoy. You know Family Guy. You don't know Dave Portnoy. I haven't watched it, so I don't know. Wait, what is Friend? It's a liquid jewelry. Bro, put it across. We're gonna do what you sound. It's out of the random scenes. I feel like this is funny. Yeah, it's just so. How do I see what you like? What comes? Wait, what? Wow, just shoot it. Just give one to five. What did I think? It's like a blue sky.
Okay, unfortunately, I don't have any paper plates, so I just run napkins instead. And cups. So feel free
Like this.
to step up and partake. Okay, so any other questions? Any other questions?
Professor.
Yes.
So the final answer for the problem we just went over
Mhm.
is the 3.92 should be
Yeah.
grams of sucrose that's going to be added to water.
Grams of sucrose, yeah.
Okay.
Mhm.
Say.
And then you would
But
still multiply that.
Mhm.
You would multiply that by 342.3, right?
To get what?
The mass of sucrose, because that's the moles.
Oh, that's the moles. Right, so you multiply this, yeah, you're right. You multiply 3.92. So let me do that down here. 3.92 grams by, what was the molar mass of sucrose?
342.3.
Oh, hold on. So this is moles. Okay, that's moles. So that means that this would be 3.92 moles multiplied by 1 mole down here. And what's the mass?
342.3.
342.3 grams And let's see what that gives. 3.92 times 342.3. And that will give you 1,300, how many sig figs? 3 sig figs, so 1,340 grams. So that's how you're gonna do that. All right?
I had a question on page 19.
Page 19. Oops, let me clear this first. Page 19. Okay, that's all the way down. Okay,
I know we did this yesterday, but would you be willing to go over it again?
okay. So basically, let me see what the question is asking. It's asking for you to calculate the binding energy, right? So just to remind you, the binding energy, the formula for calculating the binding energy is binding energy is equal to delta M times C squared. Now, delta M is the mass defect, right? The mass defect is basically the difference between the masses of all the particles in the nucleus minus the mass of the nucleus itself, right? That difference is going to be the mass defect, right? So you have to take into account the composition of the nucleus, how many protons and how many neutrons are present in the nucleus, right? So in the case of carbon-12, right, the mass number is 12, the atomic number is 6. So what that tells you is that there are 6 protons and 6 neutrons present in the carbon-12 nucleus, right? So the binding energy is the energy required to break this up into the 6 protons and 6 neutrons, right? So delta M would be the sum of the masses of all the particles present. So that would be 6 times the mass of the proton, which is here, plus 6 times the mass of the neutron, which is here. And then now we subtract from that total, the total mass of the carbon-12 nucleus, which is 12.00000 AMU. So we do the math and we end up with 0.09894 AMU. And then we multiply that. We need to convert that to kilograms. I should have mentioned this too. When you're using this equation here, the delta M must be in kilograms and the C must be in meters per second, right? In order for the binding energy to be in joules, right? Binding energy to be in joules. So if the binding energy is to be expressed in joules, then the mass must be in kilograms and the speed of light must be in meters per second. Yes, sir.
You're doing a problem like this, like on the homework, on the assignment, I think we use like 931 ME.
I was about to mention that too, right? You can use that as well, but that would have to be provided to you. What he's mentioning is the equivalence between the AMU unit and the 930 mega electron volts? Right, mega electron volts is another unit of energy, right? So there's a relationship between the AMU and the mega electron volts, right? And you can use that if the question is asking for you to calculate the answer in mega electron volts, right? I'm not sure is this in the table? Let me check. Let me see here. Let me check if that's in the tables provided. Guys, feel free to step up and partake. Don't be ashamed. Let me see here. I'm just checking to see if they have the mega electron volts equivalents to AMU. Okay, let me see. What do we have here? Okay, they don't have that. What they do have that 1 electron volt is equal to 1.60 times 10 to the minus 19 joules. That can become useful if the question is asking for you to convert from electron volts to joules or vice versa. But I don't see that 1 AMU is equal to 930 mega electron volts. So unless that is provided, I don't think you'll be required to use it. Anyway, so going back to the question, so in the absence of that relationship, we need to convert from AMU to kilograms. So in the tables, they gave you the relationship between AMU and kilograms, well, AMU and grams, which is 1.66 times 10 to the minus 24 grams is equal to 1 AMU. And then, of course, 1 kilogram is equal to 1,000 grams. So this is the setup, and therefore you can calculate the binding energy. Well, I'm sorry, not the binding energy, the mass defect, and that gives you this right here. And then you plug that into the equation I showed you before. Binding energy is equal to mass defect times c squared. We just calculated the mass defect here, that goes here, times the speed of light squared, and then you do your number crunching, and you end up with your final answer, all right? So that's basically how you do that, all right?
So the 3.00 times 10 to the 8th power is the speed of light.
Speed of light, exactly, right. And one common mistake that students tend to make in using that formula is that they forget to square the speed of light. So don't forget to do that. Okay, any other questions?
Professor.
Yep.
So if the question doesn't ask us to put the answer in mega electron volts or electron volts, then we just assume that it will be represented in
In
as
joules?
in joules, yeah, with the
Yeah, I would assume that. In fact, I would say that it doesn't matter what units you leave it in if the question did not specify. Now, if the question specified, then of course you'll have to make sure that it's converted to the appropriate units.
okay, and then that would be the kilograms to eventually get joules.
Exactly.
Okay. And also, how does the speed of light, the units cancel out?
I'm sorry?
The speed of light, the units for it, the meters over seconds?
Hold on. So let me scroll up to see what you're referring to. Okay, so you're saying what now?
The speed of light?
Yeah,
How does
3.00 times 10 to the 8 meters per second.
the units cancel out?
Oh, the units. Okay, so if I'm getting what you're asking for, you're trying to find out why is it that the units here is in joules?
Yes.
Okay, so the joule unit, and this is something that you should have learned in Chem 1. The joule unit is the same thing as kilograms meter squared over a second squared. Right? So this combination of units in this way is the same thing as the joule unit. All right? So as you can see here, you have kilograms here, and you have meters per second squared here. So when they come together, you're going to get the combination of units, which is equal to the joule unit. All right? Okay, any other questions?
Could we also go over something from assignment 2?
Assignment 2?
Yes.
Right. What question?
So it's on question number 5, letter B.
E.
Yeah, letter B of 5.
Sorry?
Letter B, where how long will it take for 90% of the N2O5 to decompose?
Hold on. You said E, there's no E here.
No, B.
E.
Yeah.
Oh, how long will it take for 90% of the N2O5 to decompose? Okay, what type of reaction is it? Okay, first order, right? So basically the equation you're gonna use for the first order reaction is Ln concentration of A over the concentration of A initial equals to minus KT, right? So T is equal to, which is what the question is asking for, minus 1 over K times Ln A over A0, right? So the question says, how long will it take for 90% of the N2O5 to decompose? What that means, therefore, is that at that time, the concentration of A would be 10% of the initial concentration of A, which would be 0.10 initial concentration of A, right? So therefore, the concentration of A over the initial concentration of A would be equal to 0.10. So therefore, we can replace all of this here with 0.10. So that's going to equal to minus 1 over K. And I think K was solved for previously, right? Let me see here.
Yeah, it was.
K would be Ln2 over the half-life. Oh, it's given here actually, right? So that's 6.32 times 10 to the minus 4. So this would be 6.32 times 10 to the minus 4. Seconds to the minus 1. Ln 0.10. And whatever that gives, that would be the answer. Okay, so the answer I got is 364. I'm sorry, 3,640. And the units here would be seconds.
Professor.
Yes.
So in this question, you did it a little bit differently, but got the same answer. Where we did the natural log of the initial concentration of A and over the natural, I'm sorry, the natural log of the initial concentration of A over the final concentration of A, and then we divided that by K. I was just wondering though,
Okay, without the minus sign?
yes, without the minus sign.
Okay, you get the same answer, yeah.
Yeah, and then it's 0.500 molarity over 0.05 molarity, and then you
Oh,
get the
okay.
natural log of that. But
Yeah,
do you
you
not
get the same
apply
answer.
do you not apply the significant figures for that if it's one significant figure for the denominator?
Uh, no, I don't think that would be one significant figure. It would still be 3 based on the 6.32 times 10 to the minus 4.
Okay, so if we have the natural log of something, we don't count sig figs.
Well, in the case of the natural log of this, strictly speaking, if you have 2 sig figs here, then whatever you get here should be written to 2 decimal places. Let me see what that gives. So based on what I have here, this should be at this part here would be minus 2.30. So if you have 2 sig figs here, this should be 2 decimal places, strictly speaking. And this has 3 sig figs, this has 3 sig figs, so this must be rounded off to 3 sig figs.
Okay, so it's like an exponent type of.
Sorry?
It's like having an exponent for something where the
No,
amount
the
of sig
exponent doesn't, you're talking about the -4?
No. I'm talking about the natural log of 0.10.
Right. The natural log of 0.10, when I did that, I got -2.30 and some other digits. So remember now, when you find the log of anything, whatever the number of sig figs of that number that you're finding the log of, you must round off your answer to the same number of decimal places.
Okay.
You go over something from assignment 8.
Okay, assignment 8. Assignment 8.
Question 22.
Okay, what question?
22.
Hmm?
22.
Okay. So in this question, it gives you the half-life of radon 222. And it says how many milligrams of a 5,000 grams. Oh, and if I remember correctly, I said that you should put a decimal point here. After 60 days, all right? Oh, shoot, I need to plug in my power cord. Okay. So the question is asking how many milligrams of the sample remains after 60 days. So the time is 60 days. And the equation that you'll use, now when it comes to half-life calculations for nuclear decay, the equation that you would use would be ln activity over initial activity is equal to minus lambda t, right? Lambda would be the decay constant, t would be the time, right? But the question itself does not give activity. But the thing is, activity is proportional to some other things, right? So activity is proportional to the number of atoms. It's also proportional to the mass, right? So because of that proportionality, we can replace the A's with M for the purposes of solving this problem. So in other words, ln M over M0 is equal to minus lambda t. So M would be the mass at that time, M0 would be the initial mass, and lambda would be the decay constant, which we have to find because lambda is equal to ln2 over half-life. So ln2 over 3.88 days, right? So let's do that first. Divided by 3.88. So I got 0.179 days to the -1. So this is going to go here. And we need to find t. So let me do this first. T is equal to -1 over lambda, ln m over m0. And then we put the numbers in, -1 over 0.179 days to the -1, multiplied by ln m, the initial mass, Oh, shoot. My bad. We're not asked for T, we're asked for M. So let me rearrange this. M is going to be equal to M0 e to the minus lambda t, right? This is what the question is asking for. So M0 is 5,000 grams times e to the minus 0.179 days to the minus 1 times 60 days. All right? So let's see here. 0.179 times 60. So I'm going to round this part off to two sig figs. I'm just going to assume a decimal point there. So this will be e to the minus 11 times 5,000 grams. So let me do that. Okay, so according to my calculation, this works out to be equal to 0.0835 grams remaining. And that's how that is done.
Is that in supposed to be in milligrams?
Yeah, you're right, milligrams. Yes, sir.
So when you find the exponent for e, so the 60 days, how do you know it's like two sig figs? Because
No, I just said that a decimal point should have been added to make it two sig figs. Yeah,
and then so when you do e to the power of -11,
yeah.
do you have to do like sig figs for that again?
Well, you have to, again, let me see here, 11, that's two sig fig, this one is kind of difficult to predict, to be perfectly honest, because in this case, you have 0 decimal places. Basically, when it comes to this, what I would do is just round off based on this here, because here's the problem with this. This has 0 decimal places, right? You can't write a number with 0 sig figs, right? The best thing to do, I would say, is basically round off your answer to the number of sig figs in the 5,000 right here. Let me do this again. In fact, because you have 4 sig figs here, I would add another digit right here. So this should be 0.08351. Yeah, so that's the best you can do as far as this is concerned. All right. Okay, any other questions?
Could we go over number 16 in assignment 4?
Assignment 4.
Yes.
This. Um. 4. And you said question number 16?
Yes, question number 16.
Okay, so in question number 16, we're dealing with a diprotic acid. What that means is that the acid has 2 hydrogen ions it can lose. So I'm just going to use H2A to represent this acid right here, right? So it can undergo the first dissociation like this. And the Ka value for this dissociation, Ka1, is equal to 7.9 times 10 to the minus 5. And then for the second dissociation, where this now loses a proton to form H plus A2 minus, the Ka2 for that is equal to 1.6 times 10 to the minus 12. So these are the two dissociations we'll be concerned with. Now the question is asking, what is the pH of a 0.10 M solution of this acid? So basically, we're going to start off with this right here, right? H2A to give H plus. Oh, and by the way, there's a second question which says, what will be the concentration of the A2 minus? All right. So to answer the first question, we start off with the first equation, right? And we set up an ice table. So initially, you're going to have 0.10 M of this. Here you're going to have 0. Here you're going to have 0. The change here is minus X. This is plus X. This is plus X. So at equilibrium, you're going to have 0.10 minus X. Here you're going to have X. Here you're going to have X. Ka1 will be equal to X squared over 0.10 minus X. And then we make an assumption. Assume that X is much less than 0.10 M, right? And based on that, we can say, therefore, that Ka1 is equal to X squared over 0.10, which means that X will be equal to the square root of Ka1 times 0.10. And Ka1 is equal to, as we said before, 7.9 times 10 to the minus 5 multiplied by 0.10. And then we find the square root. Let's see what that gives. Times 0.1. And then we find the square root. So, okay, I did something wrong. Let me do this again. 7.9 times 10 to the minus 5 times 0.1. And then we find the square root. Okay, so according to my calculation, this works out to be equal to, you have to round off the 2 sig figs. So that's 2.8 times 10 to the minus 3, right? And then, of course, we have to find a percent dissociation. Let me just squeeze that in right here. Percent dissociation would be equal to 2.8 times 10 to the minus 3 divided by the initial concentration, which is 0.10, and then multiplied by 100%. And let's see what that gives. So that gives 2.8%, which is obviously less than 5%. So that means that the assumption is okay, which means that we can go ahead and say that the concentration of X is equal to, the concentration of H plus is equal to X. So H plus is equal to that, which means that the pH is equal to minus log of 2.8 times 10 to the minus 3. So let's see what that gives. 2.8 times 10 to the minus 3. And then I find the log of that. So according to my calculation, this works out to be equal to 2.55. Right? And let me just say, you might be wondering, okay, if I calculate the concentration of H plus based on the first dissociation, what about the second dissociation? Because the second dissociation also produces H plus, right? And the answer is that that concentration will be so small that it won't affect the pH. Because the first dissociation, we know that when we make the assumption that X is less than 0.10, right? And then we find out what X is to check the assumption that's correct. We found out that the assumption is not correct, but valid. We found that 2.8%, which is a percent dissociation, is less than 5%, so that's okay. That would even be more so true for the second dissociation, right? Because if you remember, I said the Ka values, when you have more than one hydrogen ions that can be released, the Ka value for the first dissociation would be the largest, and then it falls off as the dissociation occurs in each step. And that can be clearly seen here And here, Ka1 is 7.9 times 10 to the minus 5, while Ka2 is 1.6 times 10 to the minus 12. All right? So therefore, if the first dissociation is one where the assumption is made valid, then the second dissociation would even be more so true, and therefore the concentration of H plus supplied by the second dissociation would not even be an important factor in terms of what the total pH of the solution is. All right? So that basically is the answer for the first part. I'm just going to call this A here. Now for the B part is asking for the concentration of the A2 minus. So I need to clear this here. So basically for the B part, this is the dissociation you're looking at. You're looking at H plus A2 minus, right? Now the initial concentration of HA minus, what was it? What was the H plus concentration that we had before? I just erased it.
It was 2.8 times 10 to the minus 3.
2.8 times 10 to the minus 3, right? Now, based on that first, in fact, let me just write down the first dissociation here. Based on this first dissociation, right? Because of the 1-to-1 ratio between the H plus and the HA minus, whatever the concentration of this is, the concentration of this is going to be the same. So therefore, initially, for the second step, the concentration of the HA minus is 2.8 times 10 to the minus 3, right? And this will be 0. The change here will be minus x plus x plus x. At equilibrium, you're going to have 2.8 times 10 to the minus 3 minus x. Here you're going to have 2.8 times 10 to the minus 3 plus x. And here you're going to have x, right? We can assume that x is much smaller than 2.8 times 10 to the minus 3. And we don't even have to check the assumption because, as I said before, the second dissociation would be even less significant compared to the first one, right? So assume that x is much less than 2.8 times 10 to the minus 3, then this here would be approximating to 2.8 times 10 to the minus 3. And this would also approximate to 2.8 times 10 to the minus 3. So when we write down the Ka2 expression, that would be equal to the concentration of H plus times the concentration of A2 minus divided by the concentration of HA minus, right? And because this is equal to this, right? HA minus is equal to the concentration of H plus. This is going to cancel out with that, right? So therefore, the concentration of A2 minus would be equal to the Ka2 value, which is 1.6 times 10 to the minus 12 m. And that's how we do that. All right? Any questions about this one? Or any other questions?
On assignment 2, can we do question 7?
Hold on 1 minute. Okay, assignment number 2.
Yes.
Assignment number 2. Okay. Number 7, you said?
Yes, number 7.
Okay. Okay, so this question is dealing with rate constants as affected by temperature. I think I did this one. Didn't I do this one yesterday? Anyway. Okay, now the equation that you'll be using for this question will be, there are two forms of the equation. One of them would be K1, or I should say K, is equal to A e to the minus EA over RT. And then there's another form which says ln K is equal to ln A minus EA over RT, right? Now the form that I would use would be, which one? It's asking for the activation energy. So I would use this form right here. All right? So here you're given the rate constant at a particular temperature, which by the way has to be converted to Kelvin. So this should be 273 plus this gives you 573 Kelvin. And here you have another rate constant given at another temperature, which is 230 plus 273 Kelvin. So this would be 503 Kelvin. Right? So, what I would do is I would write down two forms of this equation, one involving the first set of values and the other involving the second set of values. So ln K1 is equal to ln A minus EA over RT. And then ln K2 is equal to ln A minus EA over RT2. This should be T1, by the way. T1 here, T2 here, all right? Now, if you were to subtract the bottom from the top, then what's going to happen is that you're going to end up with, on this side of the equation, ln K1 over K2. And then on the right side of the equation, this will subtract that. And then you're going to end up with minus EA over R times 1 over T1 minus 1 over T2, right? And then now to solve for EA, that is going to be equal to R ln K1 over K2, all divided by 1 over T1 minus 1 over T2. And then we put the numbers in. Now R has to be 8.31 joules per mole Kelvin. ln K1, which is 5.7 times 10 to the minus 1, m minus 1, s minus 1. And then for K2, 2.7 times 10 to the minus 2, m minus 1, s minus 1. And then we divide all of that by 1 over T1. What's T1? T1 is 573 Kelvin minus 1 over T2, which is 503 Kelvin. And I forgot to put a minus sign, which should be here, all right? So that's the setup. It's all a matter now of plugging in the numbers. Let me erase this here. Okay, so what I'm going to do is work out this part here first. So let me do this first. So EA is equal to minus 8.31 joules per mole Kelvin. And then I'm going to work out the natural log of 5.7 times 10 to the minus 1 divided by 2.7 times 10 to the minus 2. And then that part gives you 21. And then I'm going to find a natural log of that. So when I did that, I got 3.05. All right. And then I'm going to divide by what's below. So I'm going to work out what's down here. So that's 573 minus 503, 1 over that. And I got this being equal to minus 2.43 times 10 to the minus 4. And this would be in Kelvin to the minus 1, right? So, let me do the rest now. So 8.31 times 3.05, and then I'm gonna divide that by 2.43 times 10 to the minus 4. And, okay, I did something wrong. Let me do this again. 8.31 times 3.05. And then I'm gonna divide by 2.43 times 10 to the minus 4. Okay, so I have to round this off to 3 sig figs. So the answer I got here is 1.04 times 10 to the 5. And to get the units, those will cancel out. So the final answer will be in joules per mole. And that's how that is done. All right?
Okay, thank you.
Mm-hmm. Any other questions?
For number 8, part B on the final,
Hold on, 1 minute. You're saying what now, number
8, part B.
for the final exam? Number 8. Let me clear this first. Okay, number 8. Part B, okay.
Just wondering what is like the question asking?
I'm sorry?
What is the question asking for? For this one?
Well, first the question gives you the mass of carbon-14 that you start off with, and it decays until you end up with, so you start off with 240 grams, end up with 15 grams. And this part is asking how many half-lives has this sample been through, right? So the half-life, of course, is the time taken for the substance to decrease its amount by half, right? And in the case of nuclear reactions, first order decay, the half-life is going to be constant. That doesn't change, right? So what I did, there are a couple of ways that you could do this. What I did, this is kind of more like a diagram way of representing what's happening here. I look at what happens when you divide the mass by 2 each time, right? So I start off with 240 grams here, divide by 2, you get 120, divide by 2, you get 60, divide by 2, you get 30, and then you divide by 2 again, you get 15 years, right? So that's 1, 2, 3, 4 half-lives, right? Now there's another way you could do it, using an equation which I'll admit I didn't show you guys, but this equation here is what is it again? I keep forgetting. It is N is equal to NO over 2 to the N, right? Where N is the number of half-lives, right? So, or in this case, it's mass. So you can say M is equal to MO over 2 to the N, right? So that means 2 to the N would be equal to MO over M, right? The initial mass is 240 grams. The final mass is 15 grams. So 240 divided by 15 is equal to 16, right? So 2N is equal to 16, which means that N is equal to what? 4, exactly. So that's another way of doing it. So doesn't matter which way you do it, just that's correct. Now, for this part, it's asking what is the age of the log? So basically, you need to find T, right? Now, we know what M is. We know that the initial value of M is 240. M is 15. Lambda is the half-life. So we have to calculate, I'm sorry, lambda is not a half-life. Lambda is a decay constant. We use the half-life to calculate the decay constant using this equation here, right? They gave you the half-life, which is 5,730 years. So we plug that value into this equation and we get the decay constant as being equal to 1.21 times 10 to the minus 4. And then we plug those numbers into this equation right here. And this is what we get, 2.29 times 10 to the 4. Another way of doing it is basically, and this is actually easier, basically we multiply the number of half-lives by 4. What was half-life? 5,730 years. So 4 times 5,730 gives the same answer, which is this right here, right? So that's even an easier way of doing it. All right? Is there any more questions after that one? Okay, so yeah, so that's that. Yes, sir.
You produced 3A, might have done yesterday, but
3A,
yeah.
final?
Yeah.
All right, let me we can find that. Okay. So we gave you the KC for this equation right here. And let's see. Okay. So they're asking for you to calculate the equilibrium pressure of everything, starting with this amount of phosgene. So we set up our ice table. We know that the reaction has to shift right. So that means that some of this will react to produce CO and Cl2, right? So the change here is minus X, the change here is plus X and plus X. And then we set up our, well, we get the final equilibrium terms here. We write down the equilibrium expression, which is, of course, the pressure of carbon monoxide times the pressure of chlorine, divided by the pressure of COCO2. And then we plug the terms in and we end up with this equation right here. And from here, it's a lot of algebra, right? So you have to do some manipulations here. What I did was that I cross multiply 4.63 times 10 to the minus 3 times what's within the parentheses here. And when I worked that out, I got this right here. And then what I did was that I subtract, I'll just show you here. I subtracted minus 3.52 times 10 to the minus 3 on both sides. And then I added 4.63 times 10 to the minus 3x to both sides. And this is the equation I end up with as a result of that being equal to 0, right? So you should recognize that this is a quadratic equation. And then, as I said before, you guys need to make sure that your calculators are programmed so that you can easily plug in the values of A, B, and C into your calculator and you'll get your two possible answers. In this particular case, one answer is positive, the other is negative. Of course, we ignore the negative one. And then we, based on the positive value, we can determine the pressures of everything at equilibrium. So the pressure of carbon monoxide and chlorine are both X. So therefore, we can simply say that they're both equal to what we solved for X, 0.0571 atmospheres. And in the case of the COCl2, its pressure will be equal to 0.760 minus X. So X is again 0.0571. So when we plug that number here, this is the answer we get, 0.703 atmosphere. Yes, sir.
We didn't say KC was 4.6323. You just
Hold on 1 minute.
use KC and KP as like, are they the same thing?
Oh, so yeah, you know, it's a very good point. Yeah, KP and KC won't be equal to each other. Okay, so this is what you do from this point forward. No, that can't be done. Hold on, let me see here. Okay. We'd have to find out what KP is. I mean, all of this is wrong here. Thank you for pointing that out. The relationship between KP and KC would be KP is equal to KC times RT raised to the delta N, and delta N would be 2 minus 1 because we have 2 here, 1 here. So this would be equal to KC RT, right? So basically, we're going to take the 0.76 atmospheres and multiply by 0.0821 times the temperature. What's the temperature? Did they give us a temperature?
Yeah.
527 degrees Celsius, so 527 plus 273, so 800 Kelvin would go here. Right, so that would be equal to 0.76 times 0.0821 times 800. So this would be equal to 49, how many sig figs here? This would be equal to 49.9. So what that means is that the KP that you're going to use should be right here. So this should be 49.9, which means that we'd have to solve for X using that relationship. So KP would not be equal to this, it would be equal to 49.9. And therefore you have to go through all those steps to solve for X. So again, algebra will be involved. And then, but still you'd have to use the quadratic formula to solve for this. All right, so thank you for pointing that out.
Professor,
Yes,
when you do KP is equal to KC, isn't it 4.63 times 10 to the minus 3 and not 0.760?
yeah,
So should that answer for 49.9 change then?
yeah. So this should be what 4.63 times 10 to the minus 3. So this should be 4.63 times 10 to the minus 3. So let's see what that gives. 4.63 times 10 to the minus 3 times 0.0821 times 800. So this actually should be 0.30. Again, just to make sure. 4.63 times 10 to the times 0.0821 times 800. So this should be actually 0.30. How many sig figs? 3 sig figs, so 0.304. Yeah. Which should be down here. And then you solve for X accordingly. All right. Okay, any other questions? Yes, sir.
Can you do I think it's chapter 9, just for the balancing the chemical equations?
In nuclear equations?
Yeah.
We look at the final exam. If there's any such question.
I meant like one of those up there.
Oh, you mean redox equations?
Yeah.
Oh, okay. Okay, I'm just gonna make up one. Okay, suppose you're given this. Okay, why is that doing that? Okay. So, what will be the first step in this process? Anybody?
Split them up.
Hmm?
Split them up.
Okay. So 1/2 reaction will be this. And the other one would be this. Okay, very good. What's the next step?
Make sure all the ones that aren't H and O are balanced.
Okay, so what does that mean for the first half equation?
Put 2 in front of NO3.
With a 2 in front of the NO3. What about the second half equation? Okay, good. Next step. Yes, sir.
You add hydrogens to the right side.
Not yet. There's something before you do. Before you add hydrogen, what do you balance? Oxygens. How do we balance oxygens? By adding water. So what does that mean for the first half equation? Hmm?
3 H2O on the left.
You got what?
Put 3 H2O on the left.
Exactly. Add 3 water molecules on the left. What about this equation here? To which side would you add water and how many? Four water molecules on the right. Okay, very good. Next step. The next step is what you mentioned. You balance the hydrogens by
Adding 4 for the right.
for what?
Hydrogen.
We have to be specific. It's 4 hydrogen ions. All right. And what about the second half reaction? Actually, hold on. Actually, it's more than 4. Because you have 4 here, but you have 6 here. You see what I'm saying? So that means you add how many on this side? How many H plus do you add on this side? 10 H plus. All right? What about the second half reaction? To which side would you add hydrogen ions and how many would you add?
On the left.
8 on the left. Very good. So now we get to the step where students mess up a lot. And that is to balance the charges. How do we balance the charges? Let's take the first half equation. How will you balance the charges? You guys paying attention? How would you balance the charges? You add electrons. So for the first half equation, to which side would you add electrons? Excuse me, and how many would you add? I'm sorry? 9? You sure about that? How many charges do we have total here?
8.
How many charges do we have total on the left side? 0. How many charges do we have total on the right side?
8 plus.
Plus 8, because we have 10 plus minus 2, so that's plus 8. So that means that we need to add electrons to which side? To the left or right? To the right. How many? 8 electrons, exactly. Remember, folks, you add electrons once you determine the total sum of charges on both sides. You add electrons to the side that has the higher net charge. All right? Remember that. That's where students, when they're doing this, they tend to mess up, right? They're confused about which side to add the electrons. You add the electrons to the side with the higher net charge, right? And then after you figure that out, then you add the correct number of electrons so that the total net charge on one side is equal to the total net charge on the other side. So let's do the same thing for the second half equation. To which side would you add electrons and how many would you add? What's the total charge on the left side? Plus 7, right? Because you have 8 minus 1 plus 7. What's the total charge on the right side? Excuse me. Plus 2, right? So to which side would you add electrons and how many? 5 on the left, exactly. All right? Okay, so now that we have determined or we have balanced both half equations, what's the next step? You're skipping a step. Right, you multiply because you want to ensure that the number of electrons lost and gained are the same, right? As it is right now, that's not the case, right? So the question I have for you guys is how would you ensure that the number of electrons lost and gained are the same? In other words, what do we multiply this by and what do we multiply this by in order to get the electrons being the same for both the redox, for both the oxidation and reduction?
By 5.
Multiply this by 5 and multiply this by what? 8, right? So when you multiply this by 5, you're going to get 15 water molecules plus 5 N2H4 plus, no, not plus. Then we have 5 times 2, 10 nitrate ions plus 50 H plus 40 electrons, all right? And then we multiply this by 8, so that gives you 40 electrons plus 8, 4, 32 H plus 8 MnO4 minus. And then on the right side, we have, no, I did something, hold on.
64 H plus, right? Because 8 times 8, 64.
This should be what? 8 times 5, right? Oh, yes, okay, hold on, 64, thank you, it should be 64. And then 8 MnO4, then 8 Mn2 plus 8, 4 is 32 H2O, all right. And then what do we do next? We add them up, right? But remember now, when you're adding these two together, you have to cancel out those items that are common to both sides. Okay, so obviously, the electrons will cancel out. And remember, when it comes to balancing redox reaction, there should be no electrons that are not canceled out, right? All the electrons have to be canceled out. Is there anything else that will cancel out? Okay, so these 15 water molecules will cancel off 15 of 32, which gives you 17, right? What else? Okay, so these 15, not 15, 50 hydrogen ions will cancel off 50 of these, leaving behind 14, right? So we basically need to write down what is left. So what is left would be 5N2H4 plus 14H plus 8MnO4 minus, and that's on the left side. And then on the right side, we have 10NO3 minus plus 8Mn2 plus 17 water molecules, all right? Okay, and again, as always, I tell my students, what? What do I need to do at this stage? Even though this should be the right answer, but what do we need to do? Check to make sure that everything is balanced, including the charges, right? So let's do that now. Let's start off with the nitrogens. We have 5 times 2, 10 nitrogens here on the left. We have 10 nitrogens here on the right, so that's okay. We have, in terms of the hydrogens, we have 5 times 4, that's 20. 20 plus 14 gives you what? 34, right? On this side, we have 17 times 2, 34. So the hydrogens are okay. And then we get to the manganese. We have 8 manganese here. We have 8 manganese here. So the manganese are okay. And then for the oxygens, we have 8 times 4. That's 32, right? And here we have 10 times 3. That's what? 30. 30 plus 17. Okay, so the oxygens are out of balance because, hold on, let me see. Let's see. Let me see. Okay. I made a mistake earlier up. Hold on. Yes, the mistake is right here. This is 6 water molecules. This should be 6 water molecules because we have 2 times 3, 6 oxygens. Okay, so this should be 6 water molecules here. And that will change this here. So 5 times 6, that would be 30 water molecules here. You know what? Let me erase all this down here because okay, we have to redo this part right here. 5 times all of this here, right? So when we do that, we're going to end up with 30 water molecules plus 5 N2H4 to give 10 nitrates plus 50 H plus 40 electrons. Okay, and then this one here, let me check to make sure this is straight. Okay, so multiply this by 8. So 5 8's 40 electrons plus 8 times 8 64 H plus 8 MnO4 minus to give 8 Mn2 plus 30, 8 4 is 32 water molecules. All right, so in this case, these 30 water molecules will cancel out 30 of these, leaving behind 2. The electrons will cancel out, of course. And the hydrogen ions, 50, cancel out 50 of these, leaving behind 14. Okay, so let's see what the result is. In this case, you're going to have 5N2H4 plus 14H plus plus 8 MnO4 minus. And then on the right side, you're gonna have 10 nitrate ions plus 8 Mn2 plus 2 water molecules. And let's see if this is not balanced. We have 10 nitrogens here, 10 nitrogens here. 5 times 4 is 20 plus 14, 34. Hold on, wait a minute. Okay, how are we so deficient of hydrogens on the right side? Five, 4 is 20 plus 14, that's 34, and we only have 4 here. Something is wrong. Four is 32. Okay, I'm not sure where I'm going wrong with this. I know this cannot be correct because we have too many hydrogens on the left side of this equation here. So there must be something I did wrong up earlier. Let me just do a quick check through. So when I multiply this by 5, I got 30, 5, 10, 50, and 40. And then when I multiply this by 8, I got 40, 64, 8, 8, 8, 4 is 32. Okay. And then this will cancel out. Thirty of that leaving behind 2. The 50 here will cancel out. We may have 14. Another mistake I made. This is 12 plus 4 is 16. So this should have been 16H plus. Okay. I won't have time to finish this today. What I'm going to do is I'm going to later on this evening, I'm going to post a video with the solution to this problem right here. Because I recognize the error I made earlier. This should be 12 plus 2, 14. So this should be 14H pluses here. I'm sorry, this should be 16H pluses. 12 plus 4, that gives you 16H pluses, which means I have to change that, which means I have to change a lot of other things. So I'm going to take care of this later on this evening when I get some time after lab. All right. Okay, because now we have only 5 minutes left. So unless there's a question that I can answer quickly, that's pretty much it for today.
I have a quick question, Professor.
Yes, sir.
Could we go over assignment 7, the addendum?
Okay, let me see if I can get to that. Assignment number 7, addendum. Okay, which question?
It's question number 12.
12. Okay. Silver plating occurs when electrolysis of silver sulfate is used because the silver metal is formed at the cathode, right? And we know it's a cathode because the silver ions are positively charged. So they will be attracted to the negative electrode, which is a cathode, all right? And it says this is the negative electrode. So I just answered that question. And the question is asking for the reaction, which is going to be a reduction reaction, which is Ag plus an electron to form Ag. All right? And that's basically it.
Okay, thank you.
Okay, so let me just say quickly that as far as the exam tomorrow is concerned, as I said before, there are 8 questions. Each question or each question will be based on a chapter. And I can tell you with a great degree of certainty, and I'm just using the past final here as a guide, you can rest assured that in your final, a question like this is going to be there, right? Where you're asked to find the order of a reaction or whatever, right? Where you're given the rates and you're given the concentrations at different rates, right? So a question like that is definitely going to be there. An equilibrium question will be given as well. You may be given something dealing with Le Chatelier's principle. Let me see here. And as far as acids and bases are concerned, yes, you'll get some question based on that. You'll get a Henderson-Hasselbalch equation, a titration equation, a buffer equation, which is Henderson-Hasselbalch. Solubility product for sure. Entropy and free energy and all that good stuff. And redox reactions like the one we just tried to do. As I said before, I'm going to look up do it over and post that video online. Nuclear equations and of course half-life and all that good stuff. So those are just some things that I can guarantee that will be there in the final, all right? So that's pretty much it. Tomorrow's what? Tomorrow's, I can make myself available if I know that, you know, somebody will be here or somebody needs to see me. I can make myself available in the morning. I would say that I'll be here from like 9 o'clock onwards. So you can come by my office or you can email me and let me set up a Zoom link and then we can communicate that way. All right. All right. So that's pretty much it. So I'll see you guys tomorrow.
Professor,
Yes, sir.
is the grade for test 3, is that final?
I'm sorry?
Is the grade for test number 3 final?
Oh, no. In fact, did I make an announcement? I did open a Dropbox for you guys to submit your test number 3. Let me see if I've. Okay, so apparently I did not. Hold on. Okay, so I created a Dropbox for test number 3. So you can redo it and submit it. Let me just check something here. Okay. Okay, I did open up a Dropbox. The deadline for submission of that is tomorrow at midnight. So make sure if you want to, it's all up to you, of course. You can submit it then. Let me make sure that I've uploaded that test in Canvas. Okay, I did, right, so the test is there. So feel free to attempt to do that one. And submit it by tomorrow at midnight, all right? Yes, sir.
Is that also 50% off?
Yeah. Okay, so I think that is it.
Professor,
Yeah,
so if we do this, the test 3, are we getting a maximum of 85%?
yep,
Oh, okay, so if we get over, our original score was over 85%, is there no point in doing it then?
pretty much, yeah.
Oh, okay. Thank you.
All right.
I'm still paying me the $5 for.
Oh, yeah, leave whatever contribution you can. Leave up front. Yeah, let's leave right there. Completely forgot about it. Okay, for you guys out there in Zoom, I'm signing off.